The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Thanks everybody so much for having me. My name is Tyler Lay from Oklahoma State University. Now I am going to be talking about impact of sand gradation on optimized graded concrete for pavements. Can you hear me okay? Am I too loud? I get excited. So okay, that's good. And I want to take up front. I want to acknowledge my two co-authors on this work, the two students, and I'm looking forward to doing this, like blowing a hole through the wall or something over there, and it didn't work so well. But Daniel and Ashton, they're the ones that did all the work. They've done the mixes and they've made this happen. So that they deserve a whole lot of credit. This is kind of a part 2 talk. I've talked previously at ACI about coarse aggregates, okay, and I'm not going to talk about coarse aggregates today. I'm going to talk about sands. Now, there's a big old long report that covers everything that I'll actually talk about, at the end. And if you're ever tired some night, you can start to read it, and maybe you can learn more. I want to thank the folks that actually pay the bills. There's a whole bunch of them there, and other folks that have actually given us different materials. Could not have done the work without them. I also want to give an outline of what I'm going to talk about today. Give some background on sand. Talk about this thing called the box test. Talking about coarse sand, fine sand, the tarantula curve, which Peter's already told you a bit about, and then applications in the field. So what's optimized graded concrete all about? Well, the goal is to increase the volume of the aggregate and decrease the volume of the paste. Pretty simple. Paste is binder plus water. Paste happens to be the most costly, the least sustainable, and has the biggest impact on your concrete durability. So if you can minimize paste, you're going to be doing a whole lot of good for your concrete. And just said real simply, why would you do this? You can save money. You can improve your strengths. You can improve durability, and you can improve sustainability all at the same time. You can get all 4 at once. And if you can do any one of these, that's pretty awesome. But if you can do all 4, that's totally amazing, right? So in background, you can't just add a whole lot of aggregate to your concrete mixture. It just doesn't work that way. There's a method. You have to really understand the size distribution and the volume. Okay, that's really important. And coarse aggregates happen to be crushed and sieved. David showed all the different sieve sizes that were used inside aggregates, inside pavements, and there's a whole bunch of them. But sands typically aren't. Sands typically come in a single gradation for a single source. Sand gradations vary between sources. Okay, and so because coarse aggregates are processed, we have choices. We can choose. Do we want to use some 3/8? Do we want to use 67? Do we want to use 57? We can make choices. When it comes to sands, we can't. We usually just have something. Okay. But because we have so many more choices for coarse aggregate, there's been so much more research done on that, so much more investigation to try to optimize for that. But we found the sand is equally important and has been really largely ignored. Now that's not true. I mean, there are papers out there, but there needs to be much more work done. Sand gradations. Currently, the finest modules, the FM, is the one technique that we use to actually quantify our sands. ASTM says that the FM should be between 2.3 and 3.1. Most are between 2.5 and 2.65 or so. And when the FM was actually invented, it was a great indicator. If you don't know what that is, it's a single number that summarizes your aggregate, your sand gradation. Single number that summarizes the complex shape of your sand gradation curve. Could we use a single word to describe everyone in this room? How about smart, right? That's right. Anyway, gullible? I didn't hear that. Anyway, so think about this. FM was invented in 1918 by Duff Abrams. 1918. Almost 100 years old. It served our industry a long time, but I think we'll all agree that concrete's changed a lot in 100 years. Okay? Sand, how we deal with it, really hasn't. For example, if I show a percent passing curve here versus sieve analysis down here, sieve number down here, you could say all of these mixtures all have an FM of 2.54. You're like, oh, they all look about the same. And yeah, they do to me too, because I don't like the percent passing curves that much. I'm a big fan of the percent retained. Okay? You can see so many more details. And those three curves all have an FM of 2.54. And we'll actually show today that they have very different performance if you use them inside concrete mixtures. And actually, mixtures or gradations even that look like this, absurd, crazy. There's going to be more of that coming up, craziness, right? That's fun. All three of these have an FM of 2.54. To use one number to explain the complexity of a sand curve is challenging. So that while the FM is useful, it's challenging to explain any single complex thing with a single number. And it's common to think of coarse aggregates in terms of large amounts of the large sizes and the intermediate. That's pretty common. You have large size aggregates, you have intermediate size aggregates. Why don't we do this with sand? Why don't we think of sand in terms of coarse sand and fine sand? We actually found this is really important. There's actually a big breakout in performance, a big difference between your coarse sand and your fine sand. We're going to be talking about these actually today. So what role does sand play in concrete mixtures for pavements? Well, surface finishing is a big one. Edge slumping, Peter talked a bit about that coming up. We're going to show some actual data on that. And workability. When we talk about workability for concrete pavements, we're talking about response to vibration. How does it respond when you put a vibrator inside of it? So what are our goals here? We want to determine how the distribution and the volume of fine aggregate affects the performance of a concrete mixture to be used for slip-form paving. So how the heck do we do this? Well, number one, we had to create a laboratory mixture to evaluate this workability, this response to vibration for these concrete pavements, because the slump test doesn't tell us anything about a paving mix. It can tell us consistency, but it has no other insight into workability. Other than if it's at 6, you probably don't want to pave with it. At least not slip form pave with it, right? Maybe some other things. So since the slump test doesn't tell us anything, we had to invent our own. And we're going to use this test over and over and over and over again to look at all kinds of different mixtures. And then we're going to try to develop some simple guidelines for people to use. And this is what optimized graded concrete looks like. If you haven't seen it before, this is stuff that we designed, that we have done, and it looks scary. It looks extremely scary. It looks rocky and bony. It looks crazy. You're like, the very first time they actually showed up on the job, the foreman said, no, there's a mistake. That's not my concrete. Take that away. We said, try it. Run the paver over it. When they did, it looks like that. The vibrator hits it. It flows like water. It comes out the back. It holds an edge. It's amazing. It's beautiful, beautiful, beautiful stuff. Okay? If you look at the paver, if you look at the parts of the paver, the thing that does the majority of the work, the things that consolidate your concrete, is the vibrator. It's what does all the action. And that's why we care about how does our concrete respond to vibration. Okay? That's what we're going to try to, actually investigate. But we also care about not only this, response vibration. We care about how does it hold an edge after it comes out the back. And how does it, how can you hand finish it? And what you really want when it comes to a pavement is you want a workability window. You don't want it too workable. If it's too workable, it won't hold an edge. You don't want it not workable enough, because then you can't vibrate it. You want this window. So we needed to evaluate a test and develop a test that established the window. Okay? Let's see here. And we also wanted it to be simple, because we're from Oklahoma, and we like simple stuff, right? So we're going to take this box. It's 12 inches by 12 inches by 12 inches, right? It's got an open top, it's got an open bottom, and it consists of 2 L's. You can take it apart, back and forth, 2 L's, over and over and over again, okay? These 2 L's are held together by these extremely expensive, wrong direction, expensive pipe clamps. Okay, $20. Right? And we're going to fill this up with 9.5 inches of unconsolidated concrete. We're going to take a 1-inch Stinger vibrator, not a paving vibrator, bridge deck vibrator, controlled RPMs, controlled offset on the head, 1-inch vibrator, count to 3 as we go down, count to 3 as we go out. We're going to drop the pipe clamps. We're going to take the edges of the box off. We're going to see what happens. Okay? It's actually going to hold up. It's pretty amazing stuff. This is what it looks like. So this is the concrete. You can see it being held in place. You see the vibrator coming down from the surface. And once it hits it, you can see the vibrator is influencing the concrete. That's called the sphere of influence, right? Sphere for you concrete nerds out there, right? And as the vibrator goes down, you'd like that sphere of influence to be larger. You'd like it to actually disturb the concrete, actually consolidate it all the way to the edges. But we go down and we go out. We see it's still not getting to the edges. We actually take it out. We actually take the edges off, and look at that. That's not good. Honeycombing. That means that concrete did not respond well to vibration. That mortar did not fill. That's not a good mixture. Okay? Let's look at another one. Looks similar. Vibrator goes in, sucker flows like water. It's amazing. It's amazing. Drop the edges off. It's beautiful. Look at the sides. No voids. Why are there no voids? Because it consolidated. Because the vibrator worked. Because it responded to vibration. Okay? And this is what you want. A concrete brownie. And the best mixes of all, the best ones, I can stand on. With 1 foot, like this. It's 30-minute-old concrete. It can hold me. It's amazing stuff. Okay? Now, how we evaluate these mixtures is we use a visual ranking scale. We look for surface voids. Look for what's the percentage of surface voids. And we want mixtures that don't have a lot of surface voids. We want mixtures that have something like a 2 or a 1. And we're happy with a 2. This would be something we're not happy with, 30 to 50% overall voids, over 50% voids, not happy, not good. That we would say that those would fail the box test. We also can look at edge slumping. Bottom or top, there's a mixture that did well. See the straight edges? We actually use a straight edge to evaluate these. Look at the edge slumping there from the top. That's not good. We can also look at finishability. We can take a float to it. We can see how easy it is to finish. We can compare the number of passes needed with the float to actually obtain a satisfactory finish. These are all important things, very practical things to look at when you're actually developing concrete mixtures. And we're going to use this to evaluate mixtures. So I'm going to take a mixture. Let's just follow this. We're going to mix concrete. We're going to run this slump and box test. And we're going to ask ourselves, did it pass? Now, that concrete mixture is not going to have any water reducer in it. It's just going to be typical mixture. And if it fails the box test, we're going to throw it back in the mixer. We're actually going to add water reducer in a known amount, remix it, and run it again. Evaluate it again on the box test. If it fails again, we do it again. Keep going through this loop over and over again until it passes. Once it passes, we're done. And we record the amount of water reducer it took to pass the box test. A mixture that requires a lot of water reducer is not a good mixture. It's not one we want. A mixture that requires very little, that's the stuff we're after. Why do we use water reducer? Because if we used water, we would change water cement ratio, we would change paste volume. We would change the actual volume of our mixture. If we use water reducer, we haven't changed anything. Does that make sense to people? It allows us to rank mixtures, head to head, compare mixtures. In summary, the box test. Low amounts of water reducer is good, high amounts are bad. This technique helps us establish limits. We got a really cool tool. Let's take this Porsche for a spin. What do you think, huh? Validate it though. First, we've actually used head-to-head single operators. We found we're accurate to within plus or minus 1.5 ounces per hundredweight. Multi-operators, we're accurate to plus or minus 2.5 ounces per hundredweight. The same box test performance was found if the water reducer was added up all up front or if it was added in actual small dosages. And if the sample did not pass the box test within an hour, we throw it away. We don't use it. The box test has compared well with the field paving mixes. There's more to be done on that, but it has performed well, the stuff we looked at. I have to warn you, what I'm about to show you is a little crazy. We're going to sieve sand. And you'd say, what? You will never sieve sand. That's so impractical. But our goal is to try to learn what's important. Our goal is to try to control these sand sources, to see what's critical and what's not. And sieving is the best way to get there. So we did this to better understand the critical characteristics of the fine aggregate. And I am not suggesting that you sieve your sand in practice. Okay? I'll try to be a practical guy. We're going to use 0.45 water cement ratio, 4.5 sacks. Yes, 4.5 sacks of total cementitious material. We are pushing it. 20% fly ash replacement. We're going to use a single sand source right now, a single rock quarry source, and we're going to sieve this sand to get different gradations. That's important. This is the type of stuff you can get with a box test. Okay, what we're going to do here at first, just to show you the actual power, we're going to hold these ratios the same. This is coarse aggregate. Oh, I have to apologize. I have to explain this curve. This is the sieve analysis. This is the sieve size. This is the percent retains. These are different mixtures, and this number is how many ounces per hundredweight it took to pass the box test. Now 40, that's pretty high. That's bad, right? But notice, as we lower the sand content, and as we lower the sand content, this is percent retained, so it has to total 100%. If I push down somewhere, I have to push up somewhere else. It's like a waterbed. That goes over really well in Oklahoma. They all know about waterbeds, right? So you push down over here, and it goes up over here. I'm from Oklahoma, so I can say these jokes. They go down over here, and they go up over here. And we can see that you get to this point where it's high, lower, lower, lowest, and high again. We found a sweet spot. We found a range where we've bottomed out. Found this kind of like minimum amount of ounces per hundredweight that we needed. That tells us something. That quantifies things. That allows us to compare things. We've never been able to do this before. Let's start with coarse sand. Okay? We found a very distinct difference between coarse sand, which I'm going to call between number 4 and number 30, and fine sand is number 30 and actually below. So we're going to remove all the coarse sand from the mixture. Take it all out. Every bit of it. And we're going to start adding it back slowly and see what happens. Okay? And other people have talked about minimum amounts of actual number 18, number 8 and number 16. They said, oh, it needs to be, this sum has to be, about 13%, which I think is from an old Shillstone paper. Okay, we're going to talk about this coming up. So we're going to take a mixture, very impractical. Don't do this. We take out all the 16, all the 8, all the number 4. We're going to slowly add it back. Slowly add it back. That wasn't enough. Ounces per hundredweight are too high. Got to have number 4. That's what this says. Got to have number 4. So we're going to, and actually these mixtures, they're really wild. When we don't have any intermediate, any coarse sand in there, they look like a bunch of rocks with paste around them. Looks like you almost painted the rocks gray. They're kind of crazy looking. Okay? Edge slumping is a big issue too. These things fall over. If you don't have these coarse sands in there, this 8 and this 16, you have big time edge slumping issues. Okay? Let's talk about the number 8. So we're going to leave the number 4 in. We're going to add the number 8, add the number 8. We're going to get to this point where we go from 20, 20, 5.1. Okay, that's good. That's cool. Then we're going to do the same thing with the 16. We're going to add the 16, add it in, we get 7.9, 7.5. Why am I doing this? Trying to find limits. Trying to find ranges where these things are important and where they're not. What are some takeaways from this? Look, you actually don't need number 8. You can get 7.9 ounces per hundredweight mixtures that work out that don't have any number 8 in it at all. That's kind of interesting. Okay, so what the heck is happening? What's going on? Well, remember those aggregates I showed you before? The ones that look like they just have a bunch of paint on them? As you add the intermediates, the coarse sands, and you take these rocks out of the mixture, you can see the coarse sand on the outside. They're sticking to the coarse aggregate. The coarse sand is sticking to the coarse aggregate. Okay, they're building up around the outside. These 8 and 16 seem to cling to the coarse aggregate. These smaller particles help provide much more cohesion and internal structure to the mixture, and this is important for edge slumping and the response to vibration. We'll talk more about that coming up. So if a little bit's good, well then more must be better, right? We should try to add a lot at this number 8 and number 16 and see what happens. And I'm actually really proud of this plot. I love it, in fact. We actually sieved it to get the perfect bell-shaped curve, which in every single concrete textbook is suggested as the ideal grading. It's the perfect Power 45 curve fit. And we say we didn't have some magical performance. It performed just a little bit worse than an aggregate we can get down the street. Okay. This is important, though. When I got really high amounts of this number 8 and number 16, I had finishing issues. Big time finishing issues. Okay, so let's drop it down from 16. Even at 12, horrible finishing issues. What do I mean by that? Remember those aggregates? When I showed you how they got those coarse sands kept building up around the outside of them? They look almost hairy now. They got a bunch of junk around them. Okay? When you actually go to finish these, to beat them down and finish them, you just can't. It's tough. They actually tear across the surface. You cannot have too much of these coarse sands. You cannot have too little of these coarse sands. You need to be in between. So in summary, the number 8, number 16, and number 30 contributes to the edge slumping response vibration. We needed a minimum amount of 15% accumulated on the number 8 to number 30. That's the limit. We needed at least 12% on the number 8 and number 16. Shouldn't be any more than 12% on the number 8 and number 16 to minimize finishing issues. Okay, we're done with coarse. Let's talk about the fine sand now. So we're going to do this first. We're going to take the gradation and volume of the aggregates that are held constant on everything larger than a number 16. And the volume's also held constant. We're going to allow it to actually allow the distribution to change. What do I mean? I mean, we're holding everything from the 16 up constant. It doesn't change. And everything below, the volume is constant. We're going to allow the gradation to change. And we can see as we teeter-totter around here, as we move to different places, we don't see drastic increases in water reducer dosage. So we don't see big impacts on the workability from these fine sands. Okay, we can do all kinds of stuff like this, where we can ramp these things up and down. Again, we start to get some actual surface finishing issues here. Okay, we can ramp these things up here as well. Fine sand gradation can vary largely. And the point here of all these is look at all these numbers. They're not that far different from one another. Look at these numbers. Well, as long as you stay in this range, they're not that far different. Look at these numbers. They're not that different. So the gradation can change. It doesn't really change the response. It's about the volume. It's about the volume of that fine sand. That's really important. That's what that says. Mixtures with around 20% retained on the number 36 side can cause finishing issues. We've talked about that. Fine sand gradation can vary largely without impacting the workability. It's the last thing I'm going to talk about, last topic. Let's talk about this fine sand. We're going to do one more thing to it. We're going to basically hold everything from the 16 and up constant, just like we did before. But now we're going to vary volume, and we're going to vary gradation. We're going to vary both of them. Everything over here is constant. You say, well, why does it move up and down? Because I'm changing my volume of my sand. If I take out some sand, I have to add in coarse aggregate to make it go up to 100%. Okay? And as we can see, and the point of these curves are going to look the same over and over again, is you're going to see high to a good point and then a high point again. And we had some surface finishing issues right here. We do this one here. High to good to high again. That's nice. Nice looking curve there. Do the same thing here. Do the same thing here. We see high to nice to high again. And we can summarize all this with this curve. This is the volume of fine sand. This is the water reducer dosage. These are all kinds of different gradations. These gradations changes the shape of the parabola. They change the shape of the parabola. They change how steep it is. But if you stay within these ranges, between 22 and 33%, you're going to get pretty good performance. That's what this suggests. It's pretty good insight. I haven't seen any paper that's talked about this before. And I almost do the same thing with different aggregates. We used 3 different coarse, 2 different sands, found the same thing. Found exactly the same thing. Okay? So, in summary, distribution of fine aggregate can vary largely without affecting the workability. An aggregate volume between 24 and 34% is recommended for the number 30 and number 200. The range is similar for multiple gradations and aggregate sources, and more than 20% retained on the number 30 created finishing issues. And this all leads and builds up to this tarantula curve that Peter talked about. There's more than 400 concrete mixtures that have gone into this sucker. Okay? Lots of different sources. And I've been talking about the sands down here today. Applications. 5 different ready mix producers have used this system and all seen improvements in their concrete. The new spec in Oklahoma is actually based on this actual tarantula curve. We've done 10 lane miles in Texas with this. We had used 4 3/4 total sacks of cementitious material, 30% fly ash. We saw a 10% cost savings, 25% reduction in the carbon footprint. Oklahoma estimates with this in cement content savings can be $4 million per year. That's improvement. That's cool. So in conclusion, the behavior and boundary limits of fine aggregate gradation was investigated for slip-form pavements. Talked about coarse sands contributes to edge slumping, response, vibration, finishing surface. We tried to make this simple for people. We used a minimum of 15% actually recommended on the number 8 to number 30, a maximum amount of 12% on the 8 and 16. Distribution of fine sand can vary largely without major impact on the workability. The volume of fine sand was found to be much more important, and we had this fine sand range we talked about before. At this website, optimizedgrader.com, it's where I have an actual report there. It summarizes everything that I talked about in 150 pages. I actually talked about the course as well. There's spreadsheets on there as well. Put your mix designs in, plot your curves, and show you if you're inside the tarantula curve or not. And there's my website, tylerlake.com. If there's time for questions, I'll take in. Thanks.